Okay, sorry, so we're looking at sapling. I can record some of this, you just can't see the question. Sapling homework, what do we want to call this one? The 6 solve, 7 solve? So we'll call it optical activity. Is it A through F? That's probably enough that if anybody looked it up, they'd find it. To solve for part A, what do they want you to do? Specific rotation. What is specific rotation? Okay, we're looking at standardizing a particular rotation. So if we put our compound into one spectrometer with one set of conditions and we put it into a different one at a different conditions, we're going to get the exact same specific rotation. Why would I ever want that? Well, if we're going to take a compound and we want to know something about it, those conditions, it has to do kind of along the lines with we want to know which enantiomer we have. If it changes, we're not going to be able to tell which enantiomer we have because the observed rotation changed. So we need some way to standardize and normalize our result so that when we look at a particular compound, we get the exact same answer every single time. Right? So to get the specific rotation, how do we calculate that?
Observed rotation divided by concentration and length of the container.
What's our observed rotation? Where is it? In this case, it's our positive 0.16 degrees. What's our concentration? Which we're going to address here is 0.14 molar times our path length, which was 1 decimeter. When we go through and solve, I keep thinking it's over there. When we go through and solve for specific rotation, we must use the appropriate units. The units that we have to use for concentration end up being what? Grams per milliliter. What are the units on our concentration currently? 0.14 moles per liter. We have to convert that into a grams per milliliter. Okay? So we're starting with 0.14 moles per liter. Which unit do you want to try and convert first? Moles to grams or milliliters to liters? Milliliters to liters. I like that argument too. I think that's a lot easier to do. Liters over milliliters. So my liters units can cancel. What's the conversion factor between liters and milliliters? 1,000 what? 1,000 milliliters is 1 liter. Make sure you do that conversion correctly. I can guarantee that you will see the opposite conversion show up. Okay? So you have to watch for that because you need to make sure you do that interpretation correctly. All right, so we're now in moles per milliliter. What units do we actually want? Grams. How do we convert moles into grams? Well, we need grams on top, moles on the bottom to cancel. What's the conversion factor? Thankfully, they just gave us the number. In this case, it's 155.0 grams per 1 mole. Okay. Realize that a lot of the questions that you'll see within sapling are what's known as algorithmic, meaning the numbers change. You can't just copy somebody else's numbers. Okay, so in this case, we'd have to go back to the problem, and the problem said it was 155. Yeah. This. So on an entirely different note, the spect.all file, there are some number swaps, so it's one of the issues with Word. Word swaps some numbers around on me, so I put numbers in to make it easier to interpret. I did update that spect.all file. You may have an older version, so if numbers look a little weird, check. I'm pretty sure the only difference was that numbers just appeared that didn't seem to make any sense. Okay, they just were floating around in the middle of some spectra, but They were very clearly not tied to anything. So watch out for that just in case. I'd have to take a look. Which one? So this is not as important for the recording, but for number 5 from your spect all, which is one of the more difficult ones to begin with, what's our number flow? Number 5 has an entirely different issue with it as well between those numbers. Yeah, that's something else. 132 is the right one for number 5.
132 is for what?
For number 5, 132 is the correct weight,
Oh,
I believe. So back on this problem, once we do that conversion, what can we do? We can then plug our number in and calculate what our specific rotation is going to be. Okay. Will the specific rotation ever change?
no.
I'll accept no and I'll accept yes. Why will the specific rotation never change?
Because that's the standard we set.
It's the standard for that compound. As long as the compound doesn't change, the specific rotation will never change. It's the one case where it can sort of change if we use the enantiomer. If we use the enantiomer, what happens to the specific rotation? Changes the sign. Okay? So once we know the specific rotation, any question asking about the specific rotation, we can go through and put in the same value. So question D in this case, what's the specific rotation of D after the dilution? Okay, well, I dilute it. What's the specific rotation going to be? It's still the same compound. It's going to be the exact same specific rotation. Yes?
But in the formula, the specific rotation depends on the concentration.
What happens to your observed rotation? When we move to D, your observed rotation is going to change and your concentration changes. In that change, they will cancel each other out and you get the exact same specific rotation. Okay, the specific rotation will never change for the compound.
If we don't mix it in
As long as we don't change the compound, okay, or the compound mixture. And by the compound mixture, I mean add the enantiomer. What happens, was it E? In E, what's the specific rotation of the enantiomer? It's just going to be the opposite sign. In this case, it'll be negative. So A, D, and E can all be immediately solved directly out of this with one question, okay, with A. Those would be the ones that I would really fully expect and test you on. Okay, being able to calculate your specific rotation and then realizing how it changes with that particular compound and how it changes with the enantiomer. The other calculations are looking at dilutions. Okay, so what happens if you change the concentration? Well, it's going to change the observed rotation. If we make it more concentrated, what happens to the observed rotation? It's going to increase. If we make it less concentrated, it's going to decrease. Those primary changes is what I expect you to know, okay, and be responsible for. You can go through and crunch the calculations. In the case of the homework, I expect you to go through and do those calculations to prove those differences. Yes? The strict calculations of B, C, and F, without me looking too carefully at them, no. You won't see those calculations. A, D, and E are all fair game.
what is supposed to?
What you need to realize is once you have the specific rotation, when does it change? It does not change when you change the concentration. The specific rotation does not change. What does change? The observed rotation. Okay, I know all the symbols are the same and the words sound very similar, but the specific rotation is specific. It does not change. Okay. When you change the compound to its enantiomer, you will change the sign on the specific rotation. And that is it. The magnitude stays the same, nothing else changes. Yes?
The proportion is different. One and
If you make a mixture of the S or your two enantiomers, then absolutely it's going to change, but then it's not a specific rotation anymore. When is it the specific rotation? When it's one compound. As soon as you've changed it, now what's going to happen? Now you'll record an observed rotation. What's that? As soon as you mix it, you are not looking at a specific rotation, period. Okay, for an enantiomer. What you'd be looking at is a specific rotation for a mixture, and that absolutely will change, because is it that enantiomer anymore? No, it's a mixture of them. And that's when you can go through and use your percent of excess Dealey box, which is question 6 or 7 maybe. When you look at percent compositions, where am I?
There you go.
Yeah, this one involves doing actual.
So there's not going to be any of these awesome math problems in there?
Nope.
That's the good stuff.
I will apologize. I think what ended up happening is there was a group, and for some reason in the grouping process, I must have selected do all as opposed to do two. So you ended up getting a lot more calculations than I had expected. There was one that I thought was, there's one that's a little more straightforward. You can calculate your enantiomeric excess. So in this case, this is, whoa. We're looking at sampling percent compositions from the enantiomeric excess. I'm just going to say form EE, it's close enough. Your enantiomeric excess is calculated how? Okay, it's your major contributor, or your larger minus your minor. Right, if we're told that the enantiomeric excess in this case is 81, we could now try and go through and solve for our major and minor percentages. Right, well, if one's major and one's minor, I've got two unknowns. What else do I need to know? I know that if I add the percentage of my major plus my minor, it has to equal 100%. I now have two equations, two unknowns I can go through and solve. Okay. The one extra layer of difficulty here, okay, that isn't in this question in particular, how else can we calculate the enantiomeric excess if we're given the optical activity? It's our mixture divided by our pure, and effectively 100%. Or effectively 100%. God, I keep looking at the wrong screen. That can also get us our enantiomeric excess. Once we know the enantiomeric excess, we can go through and solve our system like we've got up top. Okay? Other questions? Anything on spectroscopy? You guys really like optical activity that much? As far as time, what I would expect IR, aiming for half credit, OH, CHSP3, that's all I got. Mass spec, my M plus equals 116. How do I know it's 116? Told you that. Why did I have to tell you that? Doesn't show up on the spectrum. What happened? As soon as that molecule ionized, it completely blew apart. Okay, and we lost a big chunk right off the bat. Okay, so we've got a mass of 116. Looking at that, I see no bromine, chlorine, nitrogen, or iodine. Okay. I do expect more than this for overall mass spec, but for the complete solves, that's full credit as far as mass spec is concerned. Carbon NMR, I see 1, 2, 3, 4, 5 unique carbons. 1, 2, 3, 4 of them are alkanes. One is unknown. Oh, I definitely wrote too big. HNMR.
You got 4 unique carbons?
Five unique.
Can't see those numbers. I would probably go CH3 times 3, and I would mark that right next to the 9 hydrogen signal. And then I would move on.
Because of the 9 hydrogen.
I just got myself half credit in less than 2 minutes. And I talked. 2 minutes, I got half credit for a complete solve.
How many hydrogens?
Did I solve the answer?
No.
No. What I proved is what I know, quickly and easily, and then moved on. Get the information that you know how to work with first down. Worry about the rest later. Okay, if you got time, you can come back and fix it. Do not sit there and waste time trying to solve something, particularly if you know you're weak at it. Okay, it's only going to lead you down the wrong path. Okay? Questions about that? Okay. You'll notice there is a bunch of other stuff in this signal. But remember how I started this. I said I want to find what do I need minimally to get half credit. Minimally to get half credit is written up there right now. Done.
Nothing in the IR is required?
What's written on the IR?
Oh, I see, sorry.
I've got the IR specified. I've got mass spec specified. I've got carbon NMR specified. HNMR. I left a nasty little note for whoever gave me the problem. And then wrote whatever quick information I could interpret from it. Right? And moved on. Don't let it bog you down. Get the information that you can guarantee first and then advance. Okay? Kind of makes sense? Yeah.
How about the ones to the left of the 90?
Okay, so it sounds like there's some request to actually see a little bit more analysis in this. Erase. If I was really going to formalize this, I would definitely push this a little bit more difficultly or carefully. I see a chemical shift. I'm going to call that 0.9. My interpretation all the way at the end of that is that I have 3 CH3s. Having some kind of pseudo-advanced knowledge with this, any ideas what you might expect for a piece? Those CH3s have how many neighbors?
None.
None. How can I get 3 CH3s with no neighbors? Okay. Probably makes sense to attach them all to the same carbon. It's a pretty massive piece. Okay. I could then move to the next signal. What are we, 1.1? The 1.1 signal, I see, I would probably jump again to the integration of CH3. And I've got a zoom in telling me I have 2 neighbors, so I'm looking at a CH3, CH2. And now I've actually pushed well beyond half credit because I actually proved some analysis. And then we've got a whole mess of things following thereafter. Okay. We've got signals at, I think we got 1.3, 1.6, 2,
Okay, 2.
and 3.1. If you can't laugh, why do it? Okay. Signal at 2, if you look really carefully, you'll notice that that's not splitting. The signals at 1.3 and 1.6 are defined as complex multiplets, which means what's your multiplicity interpretation going to be?
Complex, better than 7.
Who knows? Okay. It does not mean better than 7 because it could be overlapping signals. It could be splitting of splitting. Okay. It could be splitting of splitting of splitting. I have no idea what's going on in that multiplet, so I'm going to leave it alone. Okay. Based on other information, I would probably say that I've got carbon to hydrogen. The one at 2, if we look carefully at it, does not split. Okay? It is a single peak, which means I'm looking at a singlet. But most singlets look like what? Very strong, sharp peaks. Why would I not have a sharp peak? That hydrogen has a lot of different chemical shifts, which means what we're getting is a broad signal. How can I get a hydrogen at a bunch of different energy levels?
Your ring.
It needs to be attached to an electronegative element, particularly a very electronegative element, like oxygen or nitrogen. What is that going to do to the hydrogen? It's going to start to pull the electrons in that bond, starts to oscillate a lot, and starts to interact with other oxygens and nitrogens, generating what intermolecular force? Hydrogen bonding. Hydrogen bonding is notorious for taking signals that should be nice and sharp and turning them into broad signals.
It's not a nitrogen.
It's not a nitrogen because
The molecular weight.
could go to the molecular weight, and we could also go to the IR and say the IR says it's an OH. There's my OH. Okay. The last signal at 3.1 looks like a mess. How do we get 4 peaks all equal intensity? It's splitting of splitting. Okay. It can't be overlap because the integration is only 1. Okay, so that's a kind of an odd situation. I probably have a carbon bound to a hydrogen, and to get 4 peaks all of equal intensity, we're looking at ultimately doublets. We're looking at 2 doublets. It's the only way we can get equal intensity signals.
You're saying 4 hydrogen.
So what we're looking at the hydrogens on the side, now my colored hydrogens, red and orange, are neighbors of my central carbon. Those hydrogens are different from each other. That is why we're seeing a splitting, a doublet of doublets. So if we go through to look at what that would look like, there's a doublet. If I now do another doublet on top of that, ta-da, there's that peak patterning. Is that easy? No. Well, I picked probably one of the most difficult ones to analyze. Okay. At this point, I would definitely be stuck with the HNMR. Okay. I've got a bunch of pieces that I can't analyze the splitting patterns on. Okay. I don't have a whole lot else to work with. What would I do? Go back to my IR, go back to my carbon NMR, go back to my mass spec, and see what other information I'm given. Okay? Because at this point, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons. 11 times 12? A number bigger than 116, which means I've somehow duplicated something within this structure. I need to go back and start eliminating common pieces. Okay? Not the easiest one, but I've got these pieces. On a test, this is where I would leave it. Okay? I would probably push it all the way out to this. And then maybe take a lucky stab at it and hope I got something. Okay? I won't ask this question on the test. Have some confidence in me. So you should expect an easier problem to interpret. You won't be dealing with the splitting of splitting. You won't be dealing with weird integrations or chirality within the molecule. Okay? Other questions? Sounds like you guys are all ready to go. Still got 2 minutes to talk. Okay,